Hello people, welcome to this new video. So today we gonna learn a very important topic with respect to your examination perspective of you, and of course it's quite natural to know this thing also. So before we move on to any of those videos in the upcoming session, I'd like to recommend you people to watch this video first so that you get a better insight with respect to your processor architecture, that is with respect to your ARM processor architecture. So quickly, will not waste much time spending more telling the basics here. So I will go accordingly. See, behind me you have the architecture of ARM with me. Okay, so see, don't get panicked by looking at the diagram. It's very simple, my friends. Okay, we'll try to understand the architecture, because until and unless you understand any kind of architecture of irrespective of any processor, the operations looks like simple. Okay, you feel like what's going inside, what the hell is going inside, you don't understand what is actually happening inside. So understanding the architecture, probably I should have made this earlier before this, but it's still not, it's also important. We'll see how it actually works. You know, ARM is of 32-bit. Any instruction will be of 32-bit. Okay. So where to start now? So any instruction, see, today will be in this architecture, we'll see how a single instruction is being executed. Okay, this is what the thing that we'll be discussing. So you won't go out of the track. Okay, this is what the thing that we are studying now. An instruction has to be fetched from the memory, then it has to be decoded, then it has to be executed. This is what the instruction cycle is. If the instruction has to be fetched from the memory, you need to know the address of that particular memory location. So who gives the address? It is the PC, that is your program counter. Anytime when you are executing the current instruction, the next instruction will be pointed by PC, and you know that. Which register is PC here? My R15 is the register which acts as your program counter. So the very first step is your PC gives the next address of the next instruction Okay, so here it will be passed to your address bus. If the instruction is passed to the address bus, accordingly to that particular data which is present at that instruction which is being given by the address bus, the data can be fetched. Am I correct? Okay, so PC gives the address of the next instruction, that it will be given to your data bus. Now assume that your data bus, okay, this whole is data bus. Okay, so data bus gives, of course it's a 32-bit, data bus is of 32-bit again here. Data bus will be giving you either instructions or the data. If the data bus provides instruction, it will directly be going to the control unit. See, what's the responsibility of control unit? It just controls all the things which is going to happen. It's like somewhat like brain in our human body. See, like we raise our hands, legs and all. Okay, so all the parts of the body is I think directly it is controlled by the brain, which it passes the signals. Okay, in the same way, control signals are passed to every part of the processor, so that any instruction, if it is an instruction which the data bus is providing, it will directly goes to your control unit and the control signals will be passed. Okay, there's nothing like that's it. Okay, now if the data bus provides a data, not the instruction, let us say, if the data bus provides data, so your data will be passed to your registers. You have how many registers? R0 to R15, that is totally you have about 37 registers. Out of 37 registers, 16 registers are your normal registers. Another, after 16 registers, you have registers called bank register. So let's not deviate from the topic. Your data bus provides the data. Okay, so any instruction, so the data needs to be processed now. Processed data, we call it as an instruction, okay, which is control unit is caring about. So if the raw data is being given from your data bus to your registers, okay, so register is holding your data now. What's the next step? We have two things here. One is your ALU, another one is your Mac. I'll be telling, see, don't get confused here. I'll be telling one by one so that you understand it very much properly. Okay. Why do we use ALU? ALU means arithmetic and logic unit, which performs the arithmetic and logical operations. Okay. Before ALU, you are finding in one box called shifter. I'll be telling you what is shifter is. Okay. Just bear with me for a few minutes so that I'll tell you what each and every block which is being represented over there. See, let's say you want to add two numbers or multiply two numbers. Okay, it is performed by ALU. Okay, ALU does the operations using those registers. Okay, so before I give my data to this ALU, what is the size of the data? It must be a 32-bit number. Okay, it must be a 32. Register must be a 32-bit register. Okay. So to provide, if in case whatever data which you have given to the processor is not 32-bit, let us say your data might be of 8-bit or 16-bit, let us say. Now there comes the point of sign extender. Okay, so sign extender is used to extend the data bit. Okay, let us say you have 25. So 25 is how many bits data? It is actually an 8-bit data, right? So 8-bit data we have, so it actually wants to extend this data as 0, 0, 0, 0, 0, 0 to 5. Okay. So it must be given in this way. So I want to extend my data, whether if it's 25 or any other, if it's a 16-bit number, I just want to extend my number so that it becomes a 32-bit number. Okay. So to have a 32-bit, of course it's now it's actually extending again with zeros and zeros will come back as a, will get as a 32-bit number, adding more zeros to that. Okay. So now, so sign extender is used to for those data formats which is not of 32-bit. I'll add additional numbers. I just want to give you an example. Like I think it's this example quite it holds good. So sign extender is used to add sign bit numbers for the existing data format which is not of 32 bits. Okay. After adding this particular thing, so it gives to the ALU. Okay, ALU takes the data which is of 32-bit. Let's say you want to add two numbers, 2 and 3. Okay, so 2 plus 3 gives you 5. Okay, how this addition is happened within an ALU? First, let us say we have a number of 0, 0, 0, zeros. Here I have 2. Okay. For this, I want to add 3. So, how is this 3 added? See, this register is not holding. I am not taking another register. Okay. I have an instruction called add instruction which performs the addition. So, while this addition is happening, this 2 is shifted 1 bit to its left and 3 number is added, so that it will be 0, 0, 0, 0 something, 2 and 3. And in the next register, 5 is stored, so that the sum of 2 and 3 is stored in the register. That is your added register. So, this 2 must be shifted to its left. So, who does the responsibility here? Shifter takes up the responsibility of shifting the numbers which is being required by the register. Okay. So, shifter does the shift operation over there. Okay, that is one thing. So, your ALU starts performing your operations now. I hope so you are on the track now. So ALU has started its execution. Execution might be of anything, okay, like addition, multiplication, and don't tell me division. Please bear with me, my friends. I'll be telling you why division is not possible in ARM processor. I'll be coming back at the end of, let's not go out of the track. Let's say your instruction is being executed. When the instruction is being executed, okay, let's say you are doing your multiplication. Okay, let's take a small example for multiplication. So for multiplication, I want to multiply two numbers. Okay, I want to multiply two numbers, 5 into 3, that gives you 15. Okay, so 5 is represented as what? 0 1 0 1. Okay, and 3 is represented as 0 0 1 1. Am I right? Yes. So your normal multiplication, okay, as your childhood multiplication, how you will do? So 1 into 1, that is 1 0 1 0. Next this into 1 1 0 1 0. Next 0 into anything, that is 0 0 0 0. Next again 0 into anything, that is 0 0 0 0. Okay, if I add all these things, I will get 1 1 1 1 0 0 0. Okay, so this is what I get. I hope so this is it. So what is 1 1? I am getting 15. Okay, this is your normal multiplication, which already the kids do this kind of multiplication. But what we need to observe here is, this is your multiplicand, this is your multiplier. Okay, there are two things on which you are started your operation. If you are multiplying, let's say, what is the first thing? This 1 is multiplied with all the bits of the existing number here. So it takes the results and store here. Okay, again the second bit multiplies all this and it is storing here, and third bit is storing here, fourth bit is storing here. On the board now, which I am writing now, I can able to write it in one particular way, whereas in your processor it cannot write it somewhere, it has to store somewhere, right? So that particular storing, we call this as accumulator. Okay, so accumulator is used for what? Accumulator is used to store the intermediate results. Okay, so this result is my final result. Okay, so this is your in the intermediate we want accumulator, where we store the intermediate data. So at the final we want to store this number, that is it just clumps it together, stores the final result. Okay, that is what your math does. It is, math means multiply and accumulate. Okay, so what is the input of math here? One will be your multiplicand, which is passed through your register, that is multiplicand, and also the multiplier, that is your second number to which you want to multiply, and also your accumulators. See, these are all the accumulators that we have. So math stores the final answer which is being given here, and of course after it is being stored, it is again passed the after the performance of ALU, it has been added with the math and it is sent to the register. After the register gets the total processed data, it sends back to your memory. Okay, so assume that there is memory above this board. I couldn't write clearly here. So two things happen here. You people know that two things are gonna happen here. Always it is based on load store model. Any data which you take from the data bus, we call it as load. Any data which you store to the memory, we call it as store. Okay, so we have two things: load the data from the data bus, store into the memory, we call it as storing. Okay, put the data into the memory. Now your ALU have let's say your ALU has completed its operation. If it has completed its operation, fine, it has sent back to the registers which you have. Let's say you have two things here, okay, that is your address register. I hope so you are on the track. Okay, see what is the purpose of using this address register. Let's say I have a stack here. So in the stack I have n numbers of data which is being placed here. I will move the stack, the top of the stack. Let us say the address of the top of the stack is 2000. I have the data here as 2. Let us say I want the data which is present at the location 2005. Let us say I want the data which is present at the location 2007. Let us say I want the data which is present at 2010. See here, if you observe, the series of the address is same. It is 2000 something. Okay, there's no much gap between each and everything. So your 2000 is fixed here. The starting address of the top of the stack is fixed here. So keeping this as a reference, I'm making it run to its subsequent memory locations. Let us say from 2000 move 3 address locations more, so that it goes to 2003. Move 6 locations further, so that it will point to 2006. For that we require your address register to point to the location 2000. It represents to this point 2000. See, each and every time I cannot go to the ALU and ask for your, this is what I want, again I want to go to 2006, I want to go to the location 2008, I want to go to the location blah blah blah. Okay, see, I don't want to do such nonsense things over there. Don't want to trouble my ALU here. Okay, instead I have another thing called increment here. So what is the responsibility of this incrementer here? Keeping this the actual address location. So 2000 is your actual location. If I want to move to 2006, the increments this address by 2006 such that this location is being pointed, and the irrespective of whichever data which is present inside that location is being picked out. Okay, so this is the responsibility of incrementer. I think you hope so you got this point. Okay, so see, I don't want to make the things very much complex here. Finally, you are done with this. See, this is how your processor looks like. We'll have a quick revision of whatever we have studied now. Okay, let's say, where do you start now? Where do you start your execution? Quickly, come on. We just start from PC. So program counter is responsible to give the address of the next memory location. Okay, if the PC gets as soon as the PC gives the address of memory location, it is directly taken and given to the address bus. As soon as the address bus takes the memory location, it goes to that particular memory location, takes out the data which is present at the memory location. Then comes your address bus. So address bus gives two things. One is either it gives the programs or the instructions, or it gives data. If it gives the program or the instruction, it directly goes to your control unit. Control signals are passed from the control unit. If it gives data, it is directly passed to the memory or the registers here, registers which are placed here, which is responsible for to give the input. So before giving it to the register, it checks for the data formats. If it is not of 34 bits, 32 bits, let us say, it extends the number so that it will become 32 bits. So if it is an 8 bit, it adds few more bits so that it becomes 32. If it is 16 bit, it adds another 16 bit number so that it becomes 32 bit numbers. This is done by your sign extender. After it becomes 32 bit, it is being passed to the ALU. Before ALU gets the operation, we have about minimum of 2 or 3 operands. See, there is one concept called triadic operation. See, what do you mean by triadic operations? Actually, I'm not deviating from the topic actually. I just remembered and I thought of telling you now. See, triadic operations means, let us say, I'll tell you add R0 comma R1 comma R2. It means that R0 is storing the value of R1 plus R2. Okay, means you might tell that, see, in 8086 we had only 2. Okay, add ax comma bx. So adding ax and bx, adding a and b, will the resultant value was storing in a, but now in this case in 8086 your a value was overwritten. Okay, it is used to overwrite the value, but here in this case it's not like that, my friends. R1 and R2 value is added and the resultant value is stored in the new register. Now you might ask me another question: cannot be your R0 store the same value? You can write it. Okay, if you would like to overwrite also, you can do it definitely. You can write it as add R0 comma R1, so that R0 and R1 is being added and it is stored in R0. And also you can write R0 comma R0. So you will add both R0 with R0 and you will store the final value in R0. This kind of operation we call this as triadic operation. Okay, so triadic operation is the main advantage. It's also one of the advantage of ARM processor. So let's not deviate from this. So if I want to give it to ALU, if shifting is required, so the shifter will be responsible so that it shift the number to its left side. Left shifting, we call it as the multiply, the power of 2. Okay, it will be. So if we shift the numbers from towards right side, it is divided by 2. Okay, shifting of left side is multiple of 2, shifting of right side is divided. So okay, dividing by 2. As soon as your ALU operation, during your ALU operation, if for multiplication we have the concept of MAC. So okay, what does your MAC does? Okay, during multiplication it accumulates the value and the final result will be added with your resultant value. It will be given back to a register. Okay, during the ALU, if it requires, if there is a series of numbers which is present at subsequent memory locations, which we give to the address register. So from the address register you fix the address at one particular location. If that particular address has to be incremented within a certain series, we use the incrementer there. So incrementer does the increment operation so that subsequent memory location from the base. Okay, this we call it as actually base index addressing mode. We have the topic of addressing modes. See, the concept is very much huge here, my dear friends. Okay, I would like to take up addressing mode as another topic where I'll be discussing all the 7 addressing modes within ARM. Okay, so here to be precise, with base index means what? Here you have the location 2000, which I call it as a base. From the location I am indexing to the subsequent. It's somewhat like your array concept. A of 0 is your reference. Okay, from A of 0 you are taking with the subsequent memory location, A of 1, 2 or 3 or something. Okay, so base with indexed addressing is used here, and of course after you are able to perform, it is again given back to your address bus, which is of 32 bits. So this is what the architecture of ARM is. Okay, I think it's very simple. Okay, the diagram, if you look like this and the arrow marks which is going from where to where, see, it's very simple. I think you have to practice this diagram at least minimum of 2 to 3 times before your examinations, so that there is no point of by-hearting the concept here. If you understand the concept clearly, I think you can write this diagram 2 to 3 times. You practice and you can do well, I hope so. So all the very best. Thank you. We'll come up with the next presentation. Okay, thank you. Bye.